I know that it's late. I know that I'm between you guys and the pizza that smells a lot, but I will try to go super quick. If you have any question, interrupt me, please, because I really will go quick for the interest of time. So pitfalls. I guess that Ben and the others convinced you that foundation models are great. They are here to stay, so we should start using them for everything. Should we? What happens actually if we start taking these models and start applying them to the other domains, and in our specific case, to the healthcare domain? Then we start seeing some performance drop, and in specific due to several causes. The first one is the domain gap that we have between the models that have been trained in the other tasks for vision or language as well. Task shift as well. So sometimes what we train the model for and the different applications that we can do with it could lead as well to the performance drop that we have seen. And bias and fairness. Actually, I will start with the latest one. David already introduced more or less what we mean by bias when we train the model. Here I'm giving a quick example. So basically, if we have a population with certain features, and then we start seeing subpopulations with slightly different features, and here I'm giving the example of people, but this population might even mean different types of images. When we train the model and we try to use it for prediction in terms of accuracy, we start seeing some drop in performance when we are trying to infer or to try to train for a specific task later on. So this is what we mean by bias. This is even more of a problem when we have foundation models. So you have been led to think that foundation model actually can cope with the bias because they will have more data, and due to more data, they will absorb all of the heterogeneities and be able to cope with differences in the data sets, but actually can also happen exactly the opposite, which is they will amplify and inherit some of these biases that they are learning, specifically for unbalanced training data sets when that happens. And as a consequence, then we will have models that are quite weak and cannot cope with the differences in heterogeneity in the populations that we have. And even when we try to fine-tune them, that sometimes it's not sufficiently to try to cope with these pre-training biases that we have seen. Same thing can happen with the fairness. So in this case, let's imagine that we have some training data. The images of this training data have different kind of appearances. If we are in a task like training the model in the self-supervision manner, where we are trying to kind of force the model to learn how to reconstruct certain parts, in this case of the brain. Again, this is very hypothetical. It's just an example for you guys to visualize. It might happen that we try always to optimize for the overall performance. So for certain groups of the population, once again, this won't be as optimized as possible. When we try to translate this for a new data and to do inference, the fairness will impact, and as a consequence, we will see even a higher drop in performance for these kind of models. So these models, foundation models, tend to be optimized for overall performance and not equity across the different subgroups and across the different kind of classes that we might have as well. And to do that, we can try to do a trade-off between the metrics that will favor not only the performance of the model itself, but the equity as well when we are trying to learn. We can do this through metrics. We can do this to different sampling strategies, as David introduced before, but it's important that we are aware, because once again, and as it happens for the bias, foundation models will amplify all of this lack of equity existing in the data sets. So far, so good. Am I going too quickly? No? Okay, good.
Faster.
So can speak even faster. So let's take some examples that we can actually apply to medical imaging and to healthcare data. So here I have a paper that actually took one OpenAI foundation model, in this case, CLIP. It was trained on several natural images, and then they tried to apply it to actually for X-rays to do the classification of the disease, if it exists or not in the X-rays data. To do that, they use several different data sets, and for the different data sets, we had different distributions for age, for race as well, and for gender. So the kind of model, and here very quickly, so basically they just took the visual language model that they already had from CLIP, as I mentioned, they just fine-tune it on some X-ray images, and then they measure the performance on the different data sets that I just showed. So far, so good? Yeah. So something that they start seeing when comparing this even with the radiologists is that the performance of the model actually was quite different in terms of underdiagnosis disparity. And what I want to mention by this is if I take for instance, the gender, and I compare the performance between the class that had a higher accuracy and the class that had a lower accuracy. So just by example, let's imagine that males had lower accuracy than females. The disparity here, it's basically the gap between these two accuracies. So when we see it for the different demographics and population strata, we can see that it's actually the disparity increases for the different things that we are measuring. And then when we put two things together that are already bad, it becomes even worse. And that's what's actually happened for the sex and race. So this idea that we can just take a model out of the shelf, I will just fine tune it in my data and it will work because it's a foundation model and should cope with bias, that's actually something that we are not seeing currently happening. On top of biases that we might see in terms of stratification and sampling that we have in our data sets, it might happen something differently, which is, okay, our foundation model actually was well trained, our sample strategies were okay, and now I'm trying to use this model for downstream tasks. What happens is when I try to fine tune it, even if my downstream tasks are unbalanced in terms of classes. What some researchers did actually was taking a vision language model. They tried to fine tune it as well to fill the gap between the data domain. And then they tried to test different fine tuning strategies to see what is the impact of the different fine tuning strategies into foundation models for a specific task. When they did that, they focused on two main conditions. They wanted to see what is the impact of unbalanced classes when we are fine tuning. So here we can see that we have this is a COVID data set, so we are trying to classify severity, and we can see that the ratios are quite different for the M data set, where the diseased class or the most severe class is much lower in terms of numbers than the other one. And they are also doing it for the small sample size. So one, they tested that, and even in foundation models that supposedly are quite robust and had different types of fine-tuning, and here the different colors represent different fine-tuning, we can see that the fact that we have unbalance of classes during fine-tuning quite impacts the performance. And just by using a data set that has better balance of classes, this actually fills a bit of the gap. And here I'm giving a different example, but now for the small sample size where we see exactly the same kind of behavior. So the important thing to retain here is, okay, the model might be really good. It might be trying to even cope with the different biases. I'm trying to use different fine-tuning strategies. Is that impacting my performance overall? Yes, it is. So it's not only about the model that we pick, the foundation model, if it's well trained or not. It's also how do we fine-tune it afterwards to use it in our problems. So a different example here, and this is going towards your point, Rachel, actually. It's a different study where they did something slightly different. So they didn't fine-tune the model only. So basically, they used the model that has been trained on natural images, and they apply it to diagnosis of X-rays again. And they also had a model that, on top of being trained on natural images, they fine-tuned it on medical imaging. And another one just for references that is just a VIT trained from scratch. And something that they try to see is what is the impact of fine-tuning it on medical imaging data or not fine-tuning on medical imaging data and using it straight away, but by just training the heads for the classification or the classification head. What is the impact in terms of unfairness and bias that we can see? And something that we can see here is, for instance, the models trained on natural images were much less unfair for sex, for genders, whereas the models for race, at least one of them, seems to be slightly better if trained in medical imaging data. So sometimes we think, okay, I will fix all of the problems in terms of bias and fairness if I fine-tune on images because I'm already solving the domain gap, and maybe even I have very good sampling in the medical imaging data set, and this will cope with any of the problems that we had before for the initial foundation model. That's not always true. And this is even more striking if then we do a deeper analysis and we can see that the behavior of these models in terms of disparity, it will also change depending on which kind of feature of our sample we are focusing on. Taking the example here, we can see that the accuracy disparity that we get for Black ethnicity, for instance, when we use a natural imaging trained model, it's actually going in the right direction. It means that actually from the natural images, the model was able to learn better and to be more accurate in predicting for the Black ethnicity, which is not the case for the models that have been trained for medical imaging data, or with medical imaging data, better saying. But it can happen exactly the opposite, for instance, for another population strata, which is not as much sampled in the natural imaging world, which is the case of the Asian, and in that case, the model will fail. So it's not only about, I will fine-tune it, it will solve the problems. If I cope for a population strata, it will solve the problems. No, it's really important to try to take a deep dive in understanding what is going on. And that is what another study did recently. The FarmEd paper, it's actually an attempt to establish not only benchmarking for the different foundation models that exist and that has been applied to medical imaging data, but also which metrics should we focus on to try to have a good understanding of this model is suitable for the application that I want. So I really I will skip this one, but I think it's a very good reference, and I can share the slides later just to see which kind of metrics should we be looking at when we are trying to translate foundation models to our domain. And again, for the interest of time, I will skip that. So the later one, and I'm finishing with this one actually, is, okay, answering to Rachel again and the point that she raised, is the model being wrong because it was fine-tuned and the fine-tuning actually drove it to include more bias, or is the model wrong because since the beginning was biased? And this is an interesting question that this paper asked, and I will just focus in one of the examples. So here they are using BERT, and basically this is a score, is called stereotypical score. So it tries to measure the difference between the ability of the model to predict stereotypes. So we want to get the classification closer to 50%. So flipping the coin, I cannot identify stereotypes. That's what that score in this axis represents here. And what they did first, it was, okay, let's pre-train the model. And they did it. And the score was 60%. So it was not that good. And they thought, okay, instead of just pre-training the model, because we know that foundation model by default it's biased, let's do something else. Let's try to force the model through counterfactual sampling to be de-biased for the different populations. And by doing that, the model became this part here. So the model starts being really unbiased. And that was a really good sign. And then they thought, okay, now I have my model unbiased. I want to apply it to actually a different domain. So I will fine tune it again with a different type of images. And what happened to the model in this full orange line is then it became again biased. And this highlights exactly what we were discussing before. Fine tuning sometimes it's even doing worse than it was at the beginning, or as similar as it was at the beginning. So it's really important to be bearing in mind how are we fine tuning it and why. So this paper, what they did, it's the pro-social tuning. They propose a way of fine-tuning and debiasing at the same time, instead of just doing the debiasing of the model by sampling. The way that they do is they try to estimate a prior that can inform the model of how biased is the data set that they are using. And this prior will be used later on when it's the model is being fine-tuned or trained for a specific task. I know that I'm going super quickly. I can answer questions about this model later on, but just for you to have in mind that there are already models trying to do that. And there is just one problem with these models. Yes, they reduce the bias. So the pro-social here, you can see that the bias is quite low, but they also have a drop in accuracy. So once again, there is no free lunches. It's really important to target things like bias and fairness, but it's really important to be aware that this might impact as well the accuracy. So do we want the overall accuracy, as I said at the beginning, or do we want an accuracy that's slightly lower, but actually can be better for minority groups or minority sample data? So almost there, guys.
So we are going to switch topics a bit, like so focusing on the data now. It's really looking at some of the fundamental of why we may have bias and some of the drawbacks when it comes to different tasks that can be done after we've trained our model.
Yeah, Thank you, Mark. So I'll keep this short. So here, let me see, also complicated too.
Sorry, my laptop, it's fast.
There we go, so I can also see me. So here, just very quick example. So this is a 2025 paper where the authors looked at different like classic foundation models trained on videos, and so this is more applied to surgical video data sets. And here, kind of like the obvious statement is that medical foundation model, at least foundation models that were pre-trained on a large the architecture that were trained on a large corpus of medical data usually outperforms foundation models that were trained on data sets that are sometimes 10 times fold in terms of data quantity. And so here I just outlined for one specific example. Sometimes the accuracy drop can be the orders of 20%. And so this kind of begs the question whether can you go back to kind of the more traditional kind of thinking about more the pre-training components and architectural consideration rather than just applying a just general purpose one solution fits all. And also just very nicely, I played around with Dino v3 and comparatively you have a 91% accuracy on collect 80 and Dino v3 has an 82. It was a naive implementation, but I just thought it was just for illustration purposes. Now here, kind of putting also in a position Dino, because we spoke about it. This is another paper looking at depth estimation. And what you see is kind of careful consideration within the architecture and the pre-training. You have better performance. So I won't go too much, I think we can just move on from there. It's just kind of setting the scene. And here, kind of the intuition behind this is I think we've heard a bit of Simpson's paradox, looking into bias, generally speaking. Sometimes, so usually the way we see Simpson's paradox is using a small data set will capture trends which don't exist in the general population, but the inverse is also true, right? So general trends in the general populations might not appear in the target that you are looking into. So this is, I think, just a very nice insight into why potentially you have drops in performance when you look at our smaller and more niche data. And now another thing as well that I'm kind of moving on is more in terms of application base, right? So here, very quickly, looking back at this paper, so you can see this, there's a real disparity between the average performance of models, and this is at least this is more of from intuition again. Based on pre-training regimes, which are more adapted to downstream applications, right? So if you're doing something as image reconstruction, you might be more inclined, or you might be better at doing segmentation, but the encoding that you have might not be translatable to, let's say, skills assessment or potentially relating actions. And here, this, I think, is the way you would kind of see it is if you think of your pre-training task vector, if it's orthogonal to your downstream application and no amount of fine-tuning is going to be able to you won't be able to do any transfer learning. So I mean, practice that never exists, right? You always have a bit of information that helps, but this can potentially explain where you have the performance drops and foundation model might not translate well to your application. Now, are there some can you mitigate this? So this is a very interesting paper, kind of looking back into this was more based on towards bias things, but I think you can apply it to also task and downstream application. If you think of a task vector as the difference between your pre-trained model weights and the fine-tuned one, that gives you a vector of kind of in the direction where your model needs to go. You can kind of start using this to kind of literally do model arithmetics. And here, what the paper looked into, and I think the negation one is kind of going to what Lian was touching about debiasing things, is if you have a language model trained on the internet, it might end up having some stereotypes, being racist, and you might want to remove this from your model. So what do? You train your model on Twitter, and then you remove the test vector from your language model. And then there you go. You've got a non-racist model. And so this concept you can apply to a number of different things, such as multi-learning, task analogies. So very quickly, I guess that's also what I was mentioning. Ooh, going too fast.
Chip and done, guys.
Sorry. Yes. So this is what I was explaining. But you can also think about addition, right? Addition in the sense of if you want to do potentially you have two models, and one of them is fine-tuned on image classification and the other one on object detection. You can add those vectors to have one general purpose model that can do both, rather than having to potentially pre-train on those two end tasks. And now going back to, I think this is potentially for what might be the most useful in the terms of application, actually using foundation models, task analogies, right? So here, if you think about the idea of being able to recognize, let's say, a woman, queen, and king and man, right? Potentially, what you might have a lot of access to a lot of label data for king and man and women, but not necessarily for queen, right? So what you would do is you will relate, you kind of understand that those concepts are similar. So you'll train two models, one on trying to recognize a man, but the other one on trying to recognize a king. Get those, trying to get the task vector that relates the two, and then apply that to your model that was fine-tuned on a woman, and that actually, and they showcase those results, and I really recommend you guys looking at this paper because it's a very interesting one. That you had really good performance, and that actually like opens the question of like, oh, can you do zero shot learning with this kind of stuff? Like, and for us, it will be maybe object detection and segmentation. Like we have in terms of workload, there's much less need to annotate segmentation, but bounding blocks are easier to do. So if you're understanding the relationship between these two tasks, then you just fine tune a model on an object detection and then one shot into your segmentation. So a lot of interesting questions. And to finish off my part, going back to I don't know who mentioned you and then UNet, was it Rachel? To an UNet is, well, should we use foundation models for any given task, and how much should we put effort into it? Well, for instance, NNUnit still is state of the art for most segmentation tasks, right? Regardless of whatever you come from. Medical imaging, sorry, thank you. Good point. Even more niche. I think this kind of like, at some point we're in a field where we're more interested in the application and the specific kind of environment we want to deploy our work. So for instance, like, but again, it's like how much do you, if you're like in your design consideration, would you rather like a model that performs incredibly well for your given specific application, which I think is where most of our work lies, or would you rather have a really general purpose one solution fits all, where potentially there's a trade-off between different strata of your data? And yeah, that's
as obvious from some of the discussion and some of the questions that were asked, we haven't covered all of it. It's a bit of a wide topic because now everything is full of foundation model, but there are a lot of pitfalls that has to be considered. Sustainability. I mean, there are a lot of discussion on sustainability nowadays for political reason. Then the fact that if you've got large models, as like you might be able to perturbate them. What about the data that is used? It's often been used without any copyright or by infringing copyright. You have space that are extremely large that are not necessarily specific to specific tasks. So I mean, they've got tendency to have trouble to extrapolate, to go out of samples, and then there are a few questions. I'm going to skip all of that. But that's really what we wanted to cover. So giving you a bit of I mean, we are struggling, or I am struggling with the definition of what is foundational model. So trying to really understand what they are. I'm going to skip all of that. So that's why we try to split it into 4 different blocks, covering the different blocks, giving you a bit of an idea. At the end of the day, we are not coming for a solution of what is and what is not. It's fairly blurred. As long as it's large-ish, we don't know what large is. And with a lot of data, we don't know what is a lot. You make your own definition and you define from there. There is still a massive gap between what is out there, outstream, and what's happening within our own field, up to the point that I'm not sure we've got any foundation model per se within medical imaging at the moment. We've got attempts, but really they are not, I mean, from what I've seen, they are not doing a better job than anything that will be task specific. And there is a lot of research that can be done. So on the last part that Julian mentioned, the problems that we've got issue with a different task, this is something is working on at the moment. So if people are also working on similar topic, get in touch. That might be a good opportunity to collaborate. So before I press the slides, I would like to thank the 5 of you. I'm going to press the slide. No, I could see it there. But before thanking the audience, I wanted to thank you guys. So I'd like to have a round of applause for the people. They spend a lot of time prepping for that.